All right, today we are diving into something called self-organized criticality. It's a really cool theory that uncovers a kind of hidden logic behind some of the most complex and, yeah, catastrophic events in the universe. So let's get into it.
So it all kicks off with this pretty wild question. What in the world could a single grain of sand have in common with, say, a massive earthquake or a stock market crash, or even a mass extinction? Well, it turns out the answer is pretty much everything. You know, the philosopher Soren Kierkegaard once said something that really hits this idea home. Life is understood backwards, but must be lived forwards. When we look back, history and evolution can seem like this jumbled series of events, super easy to explain after the fact, but absolutely impossible to predict.
And here's the amazing part. This isn't just some philosophical idea. Scientists have found that a ton of nature's most complex systems, we're talking everything from geology to biology, they all operate on this exact same principle. They're unpredictable, sure, but they're governed by a hidden set of rules.
So let's talk about nature's rhythms for a second. We have this idea of a gentle balance of nature, right? Well, it turns out that's often just wrong. The reality is way more dramatic.
I mean, we see it everywhere. The fossil record shows these super long periods of stability that are just shattered by sudden mass extinctions. The Earth's crust builds up stress for hundreds of years, then boom, releases it all in minutes. The sun is calm, and then it erupts with a massive solar flare. Markets seem fine until they're not.
Now, it's so tempting to look at all of this and just see random, disconnected chaos. But here's the thing. They aren't. A physicist named Purbach and his team discovered that all these chaotic outbursts actually follow a simple, universal mathematical pattern, a hidden law that ties them all together.
And to get our heads around this hidden law, we don't need a supercomputer or anything fancy. All we need is a really simple picture, a pile of sand.
So just imagine dropping sand onto a table, one tiny grain at a time. The pile gets bigger, the sides get steeper and steeper until it reaches what's called a critical state. It's basically always on the verge of collapse, and at that point, the very next grain of sand could do almost nothing, or it could trigger a huge catastrophic avalanche that changes the whole pile.
And that right there gives us our big idea, self-organized criticality. Now, that self-organized part is absolutely key. Nobody is carefully building the sandpile to be fragile. The system gets there all by itself, just by adding one grain after another. It naturally tunes itself to the edge of chaos.
So here's the crucial takeaway from this. In one of these critical systems, the giant catastrophic events aren't actually special. They're not caused by some unusually big trigger. A massive avalanche and a tiny little slip are both caused by the exact same thing, a single grain of sand. They are both just natural parts of the same process. Okay, so that's the sandpile model. It's a nice idea, but does it actually work in the real world? Well, let's start with our first big example, earthquakes.
Just think of the Earth's crust. You have these tectonic plates that are constantly pushing and grinding against each other, slowly adding stress to the whole system. That's just like us adding grains of sand. Eventually, the stress at one tiny point gives way, and it causes a little rupture. But that rupture shifts the stress to its neighbors, which might also fail, and that can trigger a chain reaction. And that chain reaction, that's the earthquake. It's the avalanche.
And this, right here, is where it gets really mind-blowing. On the left, you're seeing the sizes of avalanches in that simple computer sandpile model. On the right, that's real-world data for actual earthquakes. It's a famous pattern called the Gutenberg-Richter law. Just look at the two graphs. They are the same. A simple little model perfectly captures the dynamics of one of the most complex things on Earth. It's incredible.
But this pattern doesn't stop with rocks and geology. It also shows up on a much, much bigger scale in evolution and the entire history of life on Earth.
So, Darwin's original idea was that evolution is a slow, steady, gradual process. But when we actually look at the fossil record, we often see something different, a pattern called punctuated equilibria. This means you get these really long, stable periods where species don't change much at all, and then they're suddenly interrupted by these massive, rapid bursts of extinction and new life. And self-organized criticality gives us a stunning way to understand this. You can think of the entire ecosystem of interacting species as one gigantic sandpile. A small mutation or one species going extinct, that's like a single grain of sand. For a long, long time, the system just absorbs these little changes. But because everything is connected, the system organizes itself into that critical state, where one single extinction can trigger a massive domino effect.
a coevolutionary avalanche that we call a mass extinction.
And this brings us to a really profound, maybe even a little unsettling idea about history and, well, our own existence.
It's called the power of contingency. In a critical system, a small accident doesn't just cause a small change. It can send the whole system down a completely different path. I mean, if that one famous asteroid had missed, or if one tiny organism had evolved just a little bit differently, the entire history of life on this planet could be completely, totally unrecognizable. It makes long-term prediction basically impossible.
So we've seen this critical view in geology and biology. But the pattern is so universal. Its reach is even broader than that.
Scientists are now seeing the fingerprints of self-organized criticality everywhere, from the flickering of solar flares to the way neurons fire in our own brains, to the wild swings we see in financial markets, and even the way rivers carve out landscapes over millennia. All these incredibly complex systems seem to show the signs of a system that's always poised right on that critical edge.
So, what's the big takeaway from all this? It's that the incredible complexity we see all around us in nature, it isn't just random noise. It's an emergent property. It's what happens when simple parts interact and naturally push the entire system to a fragile, creative, and yeah, a dangerous state, the edge of chaos.
Which leaves us with a final, really powerful question to think about. If the very logic of nature is to organize itself to the brink of catastrophe, a place where tiny little triggers can have massive, unforeseeable consequences, what does that really say about our ability to predict, or manage, or control the complex systems that we all depend on?